Geodesy class. This class, which is like an introductory class, I will be taking you on geodesy and the involvement of gravity on geodesy to start with. The earth in which we are in now was originally suggested to be like a flat. But after some years, scientists and navigators came up with the earth being like a sphere, just like what you have in my hand here. This is a sphere. Because of its mathematical value, the sphere became very interesting and acceptable. But after some years, geodesists also found that the earth was not actually a sphere, but it's like an ellipsoid with flattened top, thereby having different axes, unlike a sphere that has the same axis. So the present geodesy is based on the earth being like an ellipsoid. But we still found out that there is nothing you can do about the earth other than continue to study the earth as it is. So, in the evolution of the mathematics of geodesy, you have the earth as a sphere, and later we eventually say, okay, the earth is like an ellipsoid, or rather the ellipsoid best fits the earth, best fits the earth. Now, and you know quite well on the earth surface, if you have a mass, an object, and you drop it from a height down, it will come down because of the effect of gravity. And that's where the issue of gravity comes in. Gravity has its own effect on so many things on the surface of the earth, and especially in the field of geodesy, gravity is very, very important. So we will go into the importance, the areas in which gravity has made an impact in the science of geodesy. Now, you know quite well that when we talk about the sphere, I told you because of the mathematics of the sphere, it was easy to relate the earth as a sphere. The spherical polar coordinate system indicates that you have something like this in 3 dimensions. This is Z, this is Y, and this is the X axis. So for a particle P in space within that coordinate system, you have the following recognized coordinate. This is, let's let's say this is phi, and then you have this, by the time you drop this to the xy axis, you have this being your lambda, and you have this being your r. That is the distance from the center of that coordinate system, or the spherical coordinate system, to point P. So the relation that we have here, the mathematical relation is such that we have x is equal to r sine of phi and the cos of lambda, y is the same thing as r sine of phi sine lambda, and your z will come out as this. Note fully well that your phi is your spherical co-latitude, while your lambda is your longitude, and your r is the same thing as your radial distance. So this tells us about the polar coordinate system on the sphere. Now, I hope you have written this down. Now, when we now consider the r as an ellipsoid, there is a particular coordinate system that you have for that also. Remember that this ellipsoid is derived by rotating the ellipse about its minor axis. There is an ellipse in consideration. That ellipse, when you allow it to be rotated along its minor axis, this is the minor axis, and that ellipse, the ellipse, note very well that ellipse is a two-dimensional figure. Ellipsoid is a three-dimensional figure. So when you rotate this ellipse along this minor axis round a revolution, it gives you a particular ellipsoid, which is the ellipsoid of revolution. Ellipsoid of revolution. Note it very well. That's an ellipsoid that is very, very important in geodesy and, of course, physical geodesy. Now we go into the ellipsoid. Let me clean this. We are talking about the ellipsoid of revolution. I repeat that ellipsoid is obtained by rotating the ellipse about its minor or polar axis. No, there's the best fitting ellipsoid, an ellipsoid that actually best fit this our heart. That best fitting at heart-centered ellipsoid. You can design or define it as those. That ellipsoid, of course, because it's an ellipsoid, it will have two foci. with E being the eccentricity. Of course, eccentricity is the measure of that flapping. And semi minor axis, semi major axis, and of course this eccentricity. Now, for the best fitting heart-centered ellipsoid, this E is about 522 kilometers from the center of the heart, left and right, roughly. And this B is the semi-minor axis. B is here. And we also have eccentricity, which of course is what. So, in essence, there are different formulae that can be used to, to relate this ellipsoid of interest and to organize it for us to be able to see. But let us go to the relationship between the XYZ and the phi lambda H in this. So you have these values. X is square root of U squared plus E squared sine delta cos lambda. Don't worry, I will still show you what out that one. U squared plus E squared sine delta sine lambda. Then you have Z being U cos delta. I want you to look at this figure, this diagram very well, because I will show you something about this diagram that we okay, maybe I should just draw it here. Now, you have the ellipsoid of interest there. Now, you have this and this one. This is the sphere, the bigger sphere that actually represents the sphere covering the whole heart. And you have this as the what we call confocal ellipsoid. I'll tell you later about this confocal ellipsoid. But from confocal ellipsoid to the center of the heart, you have U. That is where you have your U, which is the distance. Now, for a point of interest. Remember when we treated the sphere, we talked about a point of interest. A point of interest on this confocal ellipsoid, we actually have a projection down that has a right angle. Now, from this, from the confocal, because the confocal ellipsoid and the sphere, they are arranged in geodesy in such a way that, just like I draw it here, so you can now have from the sphere down to the center here. That's where you have, from there, you can now have your delta. Delta, and remember that this still remains your B. This one. This is still your B. And this is your A. But from here to here is your u. And so that's why you have this formula here. So this is the formula that relates your delta here is your co-latitude. It relates your co-latitude, which is the complement of reduced latitude. It's the complement of, this is the reduced latitude, so this is the complement. Your lambda remains your lambda, that's the longitude, that one does not change from then you have your he, which is of course related here, and your u, which is your confocal distance. So with this, we are good to go into the effect that gravity will actually have on points or on objects when they are on the hard surface or in the space of the heart. But before we go into that, I think it is better that we do some definitions and we do some explanation. Maybe in the next class, we'll now be able to get some fact. Now, let us do some little definition before we close this particular class. We have talked about gravity. Gravity is like, in simple terms, the force that attracts objects. So we can say it's the force that attracts objects. Of course, any two objects are, they attract each other. Let me just put it simply as that. So that force that attracts is gravity and gravitation. So gravity is different from gravitation, but they are related. The process of that attraction, the process of the attraction is gravitation. Now let us go deep into it. I can easily tell you now that gravity is what? The vector sum of gravitation. That is when you add vectorally, when you add gravitation and the centrifugal acceleration. Due to the rotation of the earth. You see, as the earth rotates, there is, for every point on the surface of the earth, there is a pull G towards the center of the earth. There's a pull. And there is also an attraction because that body is rotating with the earth. So the effect of gravitation, that's vectoral. Now vectoral addition. So this addition is not just an ordinary addition. The vectoral addition of gravitation and centrifugal acceleration due to the rotation of the earth. That is what gives us the value of gravity. Now, and we can now say that gravitation So we are going from simple definition, we are now going to geodesy definition. So gravitation, we can now say this is the attractive acceleration due to what? Due to mass. Attractive acceleration due to mass. You know quite well that when two bodies attract themselves, there is always like a mass m1 and another mass m2. Those two masses, they attract themselves. And you know from the law of Newton, which was derived from the principles derived by Kepler, that F is equal to, there's that force is equal to G m1 m2 divided by r squared, especially when they are now separated by distance r. So the more the distance, you can see from here, the more the distance, the little the effect. You can see it because r squared is down. So as the distance, but as they come together, this force becomes bigger. This is the constant. G is the constant of gravitation, and the dimension is, remember, L3 m minus 1 t minus 2. So you can go back to your physics for that particular. So now we have talked about gravity and we have talked about gravitation. Now there's an important aspect that I want you to also see, and that is the potential. Potential, you can say that's the energy that an object has due to its position in a gravitational field. Energy that an object has due to what? Due to its position in a gravitational field. So I want you to see this as very, very important. The position is very important. Energy is very important. Gravitational field is also important. So the position of any object in space is important to geodesists. Its position in space. Where exactly are you? That's why your phi, lambda, and h, they are very, very important. So you can now begin to see the link between your phi, lambda, and h and your gravitational field. So the gravitational field is very, very important. Now, let us go into what you can call, of course, you know that's potential, right? That's potential. Permit me to clean this now. I hope you are jotting down your. Don't worry, we will soon link up with what we call gravity. But now, let us just treat these three things before we end this particular class. We have talked about potential. Now, what do we now call gravity potential in geodesy? And what is gravitational potential? Remember, we have differentiated between gravity and gravitation. So here we go. Gravity potential is potential due to gravitational potential due to what? Gravity acceleration. While gravitational potential is potential due to gravitational acceleration. Good. So here, an object at I point, an object, assuming this is a ladder, up. So if you have somebody here, which you can call an object, wants to come down, that object at this I